Back in 600 BC in Greece, it was known that if you rubbed amber with fur, the amber would attract dry leaves. The word electricity derives from the Greek word for amber, which is electron. By the 16th century, there were more substances like glass that were known to attract objects after being rubbed. By the 18th century, it was known that rubbing things together produced two different entities. So let's say we have three different substances that I will label A, B, and C, and we've rubbed these substances, and then we found the following: that A and B would repel and A and C would attract. It was known that if you then took B and C, that they would attract. We now know that's because these two entities are positive and negative charges. In 1727, Ben Franklin, with some like-minded Philadelphians, formed the Junto Club. The purpose of the Junto Club was self-improvement. They would share books, get together and discuss topics that they read about, such as on natural philosophy, politics, and business. Franklin began his electrical experiments in 1747, in large part thanks to the donation of a piece of electrical equipment to the Junto Club. Here's a couple photos of that piece of apparatus. You had a crank here you could turn, which would spin this glass sphere. And then you could hold something against that glass sphere as it was spinning, like a piece of cloth, fur, or rubber, and you could build up static charge, in fact, quite a bit of static charge on the glass sphere. Franklin charged up his glass sphere, and when he brought a conductor closer and closer to it, he got to a point where he would get a spark across the gap between the glass sphere and his conductor. Franklin observed that the distance at which he obtained a spark became larger as his conductor became sharper. This gave him the idea for the invention of the lightning rod. Distributed on the top of tall buildings are all these metal rods that are electrically connected, and then they're electrically connected to ground. Here is a photo of one of those rods and electrical connections to adjacent rods. A lightning strike would hit one of these rods, and then the current would flow to ground. Franklin also observed that the force between two objects depended on the separation, and also that the more charge on an object, the greater the force. So Franklin had all the qualitative understanding of what Coulomb's law describes in terms of forces between charged objects, but he didn't have the capability to make the sensitive measurements to come up with Coulomb's law. When you rub two objects together, they become charged. It is usually attributed to the friction caused by the rubbing. It's actually just the contact between the two materials that results in charge transfer. The rubbing just enhances the amount of contact between the two objects. Franklin theorized that when two objects touched, an electric fluid would flow from one object to the other. When glass and rubber are touched, Franklin didn't know the direction of the electric fluid, but he just guessed that it would flow from the rubber to the glass. So he termed the glass as becoming positive because the amount of electric fluid was increasing in the glass, and he called the rubber negative because the amount of electric fluid was decreasing. It turns out when glass and rubber are touched, it's actually electrons that are flowing from the glass to the rubber. But Franklin's convention has held, so we think of current flow as flow of positive charge, even if the current flow is due to electrons flowing in the other direction. When two objects are touched, there's a transfer of charge. So when glass is touched to rubber, the glass becomes positive and the rubber becomes negatively charged. Materials can be ranked in the triboelectric series. So if you take any two objects and touch them, the one higher up in the series will become positively charged and the one lower in the series will become negatively charged. So if you touch aluminum to copper, the aluminum will become positively charged and the copper will become negatively charged. The reason electrons transfer from the aluminum to the copper is that the copper holds on to electrons more strongly than the aluminum does. We say there's a chemical potential between the aluminum and copper that will drive the electrons from the aluminum to the copper. Let's assume the aluminum and copper are initially uncharged, so there's no electrical potential between them, and we're going to bring them into contact. I'm leaving a gap to illustrate what happens at the interface, but assume that the aluminum and copper are in contact. The chemical potential will result in electrons flowing from the aluminum to the copper. The copper will take on a negative charge and the aluminum will take on a positive charge. So now there's going to build up an electrical potential that will drive electrons from the copper to the aluminum. The system of the aluminum in contact with the copper will come into equilibrium when the electron flow due to the chemical potential is balanced by the electron flow due to the electrical potential. In equilibrium, every process and its inverse process are in balance. The sum of the electrical potential plus the chemical potential is what we call the electrochemical potential. In equilibrium, when the aluminum is in equilibrium with the copper, it's the electrochemical potential that's going to be zero. There's still an electric potential and a chemical potential, but the sum of those two is zero in equilibrium. If you've taken 305, you're familiar with the electrochemical potential, and it's usually referred to as the Fermi energy level. If you could maintain the initial non-zero electrochemical potential difference, you could get a continuous flow of charge and in essence have a battery. In the next video entitled Voltaic Pile, I will demonstrate and further explain how you can make a battery from aluminum and copper. The reason the rubbed amber would pick up dry leaves is because of electrostatic induction. Electrostatic induction is the redistribution of charge on an object caused by the influence of nearby charge. In another video entitled Static Charge and Electrostatic Induction, I will demonstrate and further explain electrostatic induction.